Okay. Yes, we did chapter 17. We did finish chapter 17. So let's real quick recap what we did at the end. So the only thing left for chapter 17 that we didn't cover was lactones and lactams. So we are pretty much done with that. The only thing I will cover, it was in the cheat sheet, so I didn't want to spend time on it last time because you guys were tired and all that jazz. But I do want to mention in chapter 17, every reaction doesn't have a name like we did in 16 and we're going to see in 18, but there's two names you need to know. So if we are creating an ester, it's called an esterification. So making an ester, esterification. And if you're going from one ester to a different ester, so we went from, this ethyl group to this group, that's called a trans-esterification because you're going from one ester to another. And whenever we turn an ester into a carboxylic acid using base, we call that a saponification. Those aren't like huge like things like you need to know the name and the reagents and everything. Just kind of understand esterification. So the Fisher stuff he was talking about, I believe he was just going over this reaction in more detail, but we already kind of covered the reaction mechanism. It's going to be exactly the same as all the other chapter 17 ones. It just has the specific name. Is that what you're talking about? Or, okay, yeah, cool. What else? And yeah, that was pretty much it. We've talked about everything else and we've done all these different examples. So pretty much done with chapter 17. Now the fun stuff, chapter 18, is it feels like it's really different from 16 and 17, but in reality, it's the same concept, just the mechanism looks a little bit different. So it can be overwhelming at first, but it's not too terrible. And someone said to go back. Do you want to go back to the handout or the cheat sheet? Let's go to this, I guess. This, okay. So this is something I sent you guys. So you don't have to like, yeah, the reactions. What's up? Oh, not this. Okay, so I'm guessing this one then? Okay. You're very welcome. Okay. So back to 18. So we've done a lot of different reactions. We're going to talk about tautomerization. So I'm going to write that in big letters. Tautomerization. And we're going to talk all about what that means, what that is, and why we have a whole chapter dedicated to that. So just like chapter 16, we're going to start with a ketone. That was an ugly line. And gasp, I'm giving you an asymmetrical ketone. And the only reagent I'm going to give you is NaOH. So we know that Na is plus, so that means OH has to be minus. I don't know why there's screaming in the background, but I hope that's not disruptive to you guys. So anything with a negative charge is a what or a what? A nucleophile or a base. Cool. So, have we ever seen an OH being a nucleophile in the reactions we've done this semester? Yes, we have, such as the gem-diol reaction, right? Except we only have base this time. We don't have any kind of catalyst. We don't even have H2O, so we don't have anything to like stabilize this charge. So it doesn't really look like being a nucleophile is going to be very efficient. So the other thing it could be is a base. Are there any acidic hydrogens to steal from here? Okay, someone said no. Someone said maybe at the end. So let's draw out some hydrogens. Bam, 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 bam. So this set and this set, what do they have in common? Oh, first of all, that's way too many hydrogens. So what's a similarity in the two sets of red hydrogens? They're on alpha carbons, exactly. So let's call this alpha 1 and alpha 2. All right, so something I want you to notice is if we have a double bond and we have something on the adjacent carbon, what is a fancy little name for that position besides the alpha position? Think back to acidity trends. If you have no idea what I could be talking about, that's okay, but I want you to think about it for a moment. Okay, restate the question. So we talked previously about having something along this line. This could be any kind of double bond. And we said that the position right here has a specific name. What is that called? So let's say we have a chlorine here. It's the allylic position, exactly. So the same thing applies when we have a carbonyl. So the alpha position is also an allylic position. And so I'm going to erase this because this doesn't really matter. It was just to get you guys thinking. I'm going to take this and I'm going to keep it here. So what do we know about the allylic position? So someone said sp2, and that's a great point. So it's not necessarily sp2 yet, but the reason that that position is acidic is because once we take that hydrogen, it becomes sp2, and we have resonance with the oxygen. That was a lot of words I just said, so I'm going to draw out a picture for it. So let's say we take the hydrogen, right? And I'm going to say a generic base comes in, steals that hydrogen, gives those electrons. Now we get two H's and a negative charge. We know that cations, anions, and radicals are sp2, and sp2 carbons can do resonance. So that negative charge is stabilized through resonance. And that is something I'm saying, right? Those are just words. So why do we consider this to be more stable than this? The more substituted double bond, but something a little bit more than that. Yes, perfect. So the charge lands on the oxygen. So oxygen is much better at holding a charge than carbon is because it's more electronegative. And I'll write here, O is better at holding the charge. So let me zoom out a tad. So this is kind of like a review note. This is not necessarily unique to this reaction. This is just something you should know about acidity. So remember when I told you throughout the semester, you're never gonna take a hydrogen off of a carbon, you're never gonna break a carbon-carbon bond until the end of the semester. So we've reached the end of the semester. So now we're able to steal those hydrogens directly off of carbons. So let's zoom back into our reaction here. All of this to say, these alpha hydrogens are in the allylic position, so they're acidic enough for the OH to act like a base and steal one. So I'm going to say this will react as a base. Now, you guys were talking about the substituents on the double bond and everything. So based on what we just talked about, which alpha hydrogen do you think is going to be stolen? Alpha 1 or alpha 2? Alpha 2, I absolutely agree. So let's go ahead and I'm just going to draw this slightly further away so the arrows don't look ugly. So we snatch that hydrogen, we give these electrons to this carbon. And now we get nothing has happened to the double bond yet. We have one hydrogen left, and we have this pair of electrons, right? So let's zoom back out. We said, based on this little note here, that we can do resonance, and we can bring these electrons here and bring those electrons up here. Do we all agree that that resonance structure will be more stable because the oxygen holds the charge? Yay or nay? Yes. Ooh, we got a no. Okay, so let's draw it out and then let's talk about it. So I'm just going to move this so it doesn't disrupt our reaction, but I'm not going to like delete it or anything. What have I done? So sorry. I have this terrible fear that all the zooming in and out gives people motion sickness, so I hope that nobody feels that way. All right, so what we end up getting if we do this resonance is we get O with a single bond. We have one hydrogen still here, and now we have a negative charge on the oxygen, and we have a double bond. And yes, so someone asked me to re-explain something about acidity. I can definitely do that, but let's finish this reaction step first, and then let's go back to it. All right, so in this step, we did resonance. We brought these electrons here, creating a double bond. And now we put the electrons on the oxygen so it has a negative charge. If we look at what we have left in our reaction mixture, excuse me, I can't speak today, we created a molecule of H2O. The easiest way to make this guy nice and neutral is for it to steal back that hydrogen. So we end up getting OH. We have one hydrogen left on alpha 2. And we have this double bond. So I'm going to zoom out so you can see the whole reaction. It's only a few steps, not too wild. Wow, I keep joking. Not too wild, I hope. And I will give you a moment. All right, so we talked about how, I'm going to change the color of this for a moment. We talked about how these two are a pair of resonance structures, right? So let's go ahead and label. They are resonance structures. And this pair of resonance structures actually has a name. It's called the enol 8. And this final product is called the enol. The way we remember those two names is we have an alkene plus an alcohol. We get an enol. For the intermediate, it's an alkene plus an alcohol plus a negative. And a negative charge usually gets the suffix 8. So we get an enol 8. So let me zoom out so you can see those together. That was a mouthful. So now we have our ketone, which is just our regular old starting material. We have our enolate, and then we have our enol. Someone said that color is bomb. The purple gray mix color scheme is my favorite. I love it a lot. All right, so we're actually going to talk about another pair, and there's entirely too many things going on here, but that is okay. So this right here, we're going to call our tautomeric pair. So it's the ketone enol tautomer pair. And the difference between a pair of resonance no, so you're right. Let me just draw these out a little bit better. So that only counts this much. All right, so the difference between the enolate, which is a pair of resonance structures, and the tautomeric pair, which is a pair of tautomers, is in resonance structures, we just have a flow of electrons across a molecule. So this doesn't require an actual reaction to be happening. That's just like the free flow of electrons. That's what naturally happens. Versus tautomers, I'm going to zoom in again. Tautomerization is the movement of a hydrogen from one position to another on a molecule via acid. Oopsie. I'm going to move this down just so I don't run out of room. I'm so sorry. So we're going to say this is a movement of a hydrogen from one position to another on the same molecule via a reaction with acid or base. And I'm going to zoom back out so you can see the whole thing together. So, to recap, this whole reaction is called a tautomerization, and we're going from a ketone to an enol. In this version, I showed you a base. Later on, we'll see an example with an acid, but it's the same product. The enolate is the intermediate, and that is a pair of resonance structures. And a pair of resonance structures is just showing the flow of electrons throughout a molecule. Whereas a tautomer, a pair of tautomers, requires an actual reaction to happen, and that reaction has to be through acid or base. And that's when a hydrogen is physically removed from one position and added to a different position. I know that was a lot and there haven't been many comments. So how do we feel so far? Does this feel okay-ish? And I'm just going to go ahead and make this a little bit thicker just so everything matches. So let's say 0 is I have no idea what you're talking about, and 5 is, oh, this is easy peasy. How do we feel so far? Wow, 3.5, 4, 4, super, 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 super. That makes me so happy. Okay, so let's go back down here and talk about the acidity for a second. So the alpha position and the allylic position are the same for this kind of reaction. So the allylic position is just next to a double bond. And the reason it's super acidic is because once we take this hydrogen off, we get a negative charge, right? That in and of itself is not super good. But the fact that that can perform resonance with this carbonyl means that we can move the charge to the oxygen, which is much more stable than just having a charge here. So if we were to compare this to just, let's say, if this was only carbons, right? And we had hydrogen, hydrogen, hydrogen. A base is not going to want to take that hydrogen because we're just left with this. And there's no resonance that it could do. There's no stabilization, nothing like that. Whereas here, it can drop these electrons, move it around, and we get a more stable molecule. Does that make a little bit more sense about why that position is acidic? Yeah, so the question was, so usually acidity is resonance stabilized and basicity isn't. So I'll say yes, because when we think about acidity, resonance is a big part of that. But as far as bases go, we're going to focus more on just electronegativity and charge. So we're not really going to focus on resonance. But in the grand scheme of chemistry, I'm sure it does play a role. We don't care about it in this class. Okay, you're very welcome. So here, let me erase this and let y'all take a picture or take notes or do whatever it is that you would like. It's kind of far away, so if you guys can't see, I'll try to zoom in a little bit. Bam. Do. Yes, I can definitely zoom in to this part. Okay, so let's go back up here to the handout, the first page. So we basically went over all of these questions and we answered them. So just to recap, tautomers are a pair of isomers where the hydrogen was moved from one place to another. Tautomers are different from resonance structures because this needs a reaction, this does not. We know that the ketone and the enol are tautomers, and we already drew out the mechanism. So now we're going to move on to something called racimization. So we're going to go back down here actually for racimization. We're going to take this same exact idea and we're going to redraw it just a little bit differently. So we have this. Let's do NaOH again, just because, why not? Right? And you already told me last time that we're going to steal this hydrogen. These electrons go here. And while I'm drawing that, yes, tautomers need a reaction to happen, so they need an acid or a base to set off a reaction, whereas resonance structures, the electrons just move around freely. You are absolutely correct. All right, so at this point, we had a negative charge. So what is this intermediate called? The enolate, perfect. So we do this, right? And we get a negative charge on here. We get a hydrogen. We get this. And the last step was we take the H2O and we protonate. So I just drew out the exact same reaction. I just did it linearly instead of in that like square. And we get this. So same exact reaction. Nothing has changed. We just went from a ketone to an enol. But something that's really interesting about tautomerization is that it goes back and forth. So it is a reaction that goes back and forth, but it needs acid or base to move back and forth. So once we get here, we're going to eventually just use that OH to attack and reverse the whole reaction. Why is that important? Well, what is the hybridization of those two carbons? sp2. Exactly. So sp2, 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 sp2. So if at any point in this reaction we started going backwards, is there any way to maintain any kind of stereoselectivity or stereospecificity, which is a mouthful? I got a yes question mark? A possibly? Well, let's think about it, right? So when you have a double bond and a double bond goes through any kind of nucleophilic reaction, is there any way to differentiate, will the nucleophile attack from on top or will it attack from the bottom? We got a maybe. Okay, so when we have double bonds, those double bonds are planar, right? So if we have something like this, right? Let's pretend this looks like it's on a plane. And we have a nucleophile coming to attack. That nucleophile can come from above and it can come from below. So there's no way to really differentiate which side it'll come from unless we had big bulky groups or whatever. So the same exact thing is going to apply here. So all of these guys are completely planar. So another way to represent that is I can draw these as wedged and dashed to show that they're on two different planes. This is 3D, but once we get to this step, it's completely 2D. So let's imagine that instead of going the red route, we went the pink route. And instead of doing resonance, instead of doing anything like that, we're going to steal back, or you know what, let's do it from this step. I drew the arrow wrong, I'm so sorry. So instead of using the H2O to, no, let's do it from this step. I'm so sorry. I'm a mess right now. So instead of using the H2O to protonate, we're going to actually steal a hydrogen from the H2O. So we go like so. And if it looks like way too much in one drawing, we can redraw it. That's kind of why I was trying not to have too many arrows in one place, but we could have also done this instead. So if we went the pink route, we would have gotten two different answers. So either the hydrogen could have been re-added dashed, or it could have been re-added wedged. And we have no way to differentiate or select for one of those options. Does this sort of kind of make sense what I'm saying? I don't know how you guys feel. I just feel like this whole thing might be a little bit overwhelming with all the arrows. So if you are having any trouble with it, please let me know. It makes sense? Okay, cool. So all of this setup, all of this stuff is to say we have equal amounts of this isomer and equal amounts of this isomer. So we could call this a what kind of mixture? Racemic, yay! So we're going to call this a racemic mix. So let me delete this. So since we can form a racemic mix, we're going to call this a racimization. So to keep it simple, I showed you guys an example where both of these were hydrogens, right? But in reality, we know that to be chiral, there has to be 4 different groups. So let's go ahead and call this, instead of a hydrogen, let's call it an ethyl group. So nothing at all would change. Now instead of 2 hydrogens, we simply had 1 hydrogen and 1 ethyl. Any questions? Someone said I'm lost, but I'll watch the video again. While that's valid, I'm sorry that you're lost. I know it is a lot. So kind of just think about it as the racimization is not a new reaction. It's the exact same thing that's already happening. We know this is going back and forth and back and forth. So if we start with a chiral molecule, when we go about this reaction, going backwards, we cannot maintain the stereochemistry because we have sp2 here. So that means we're just going to end up with a racemic mix of our starting material. And a little note I'm going to write that's very important. What you need for a racemic or a racemization reaction is you need a chiral alpha carbon with a hydrogen. So if I give you something like this, like this, and like this. And let's call this A, B, C, and D. Which one of these can undergo a racemization? Ooh, we got two C's, we got one B. All right, so, okay, we got someone who said B or C. You guys fell into my trap, and I am very happy that you did. So let's talk about it. Someone said C or A. Ooh, okay. So we said we need a chiral alpha carbon. So that's the first thing. Is this chiral? Yay or nay? Ooh, we got a 50-50. So this actually is not chiral. Yes, because we have two methyl groups. So to be chiral, you need 4 unique groups. In this one, we only have 1, 2, 3, and then we have 2 methyls. So those are the same. Is this one chiral? No, because I gave you the same exact molecule, but I drew in wedges and dashes, and he will do exactly that on the test, and it does fool a bunch of people. So again, this is just 2 methyls, so that's not chiral. Let's look at C. Is C chiral? Okay. No, it's not, because again, these are 2 ethyls, but let's add another carbon here. Now, is it chiral? Yes. Okay. So can C undergo racemization now? And someone said, why is it chiral? Now it's chiral because we have 1 methyl, 1 ethyl, 1 propyl, and the carbonyl. So these are 4 completely different groups. Can this undergo... No, don't apologize. I love questions. Okay, so can this undergo racemization? It's racemic. It's chiral. Okay, we got a couple yeses. Let's check this last one. Is this carbon chiral? Yes, yes it is. Okay, so We know that A and B are out because they're not chiral. C and D are chiral, but you can't forget this second half with a hydrogen. Does C have an alpha hydrogen? No, it does not. So this cannot undergo a racimization because it's no alpha hydrogen at the chiral center. This last one, however, we have 1, 2, 3, 4 different groups. So it's chiral. We have a hydrogen. So D is the only one that can undergo racimization. And yes, I can show the different groups. So we have a methyl here. That's number 1. We have this carbonyl. That's number 2. We have this chain. That's number 3. And then we have the hydrogen. That's number 4. Okay, cool. So since we have to have a chiral alpha carbon with a hydrogen present, only D would be able to undergo racimization. And let's scroll up to the handout part. I have another question that's very similar, and so we're going to summarize today's session by doing this question. Please tell me which one of these guys can undergo racimization. Okay, we got a couple answers, and they're all correct. Yay! Okay, so if you didn't get it, that's okay. C is the right answer. And that is because if we look at all of the alpha carbons, the most obvious ones to see, in my opinion, are D and B. So we know that there's 2 hydrogens here. There's 3 hydrogens here. So we know that neither of those positions are chiral. In D, again, same exact situation. We know that that's not chiral because it has multiple of the same groups. And then between A and C, those are almost exactly the same. So why did you pick C instead of A? Yes! So there is no hydrogen on A. These are 4 separate groups, but none of them are a hydrogen. So this is the only one with a hydrogen on a chiral alpha carbon. Exactly. Yes, it has to be a single hydrogen bonded to a chiral carbon. Yes. Yay! Okay, so we covered a lot today. You guys did amazing. I loved all the participation. I'm sorry for tricking you a couple times. But yeah, that's all I have for you today. I will see you next week. And I will, as always, stick around for another minute or so in case anyone has any questions, comments, or concerns.